Pues vamos a empezar. Hola a quienes están aquí acompañándonos en el Zoom, las personas que integran SOMA, la Sociedad Mexicana de Astrobiología, y a las personas que nos acompañan en nuestra transmisión en vivo por YouTube. Estamos estrenando canal de YouTube, así que nos da mucho gusto. Esta va a ser nuestra primera transmisión y también es la primera sesión de una serie de charlas que hemos titulado Astrobiología para todas y todos y todas. Entonces, pues esperamos que les guste. Vamos a hacerlo una vez al mes. En principio va a ser los jueves, el día de hoy por única ocasión va a ser el viernes, pero en principio pues lo vamos a hacer los jueves. Entonces les voy a presentar, hoy tenemos el gusto de recibir con nosotras a el doctor Andrea Miglio. Él es de origen italiano, realizó sus estudios de licenciatura en física en la Universidad de Milán. También se doctoró en física, pero ahí en la Universidad de Lieja, en Bélgica, y durante un tiempo estuvo trabajando como postdoctorado en la misma Universidad de Lieja y luego migró a Birmingham, Estados Unidos, donde estuvo trabajando en diferentes posiciones dentro de la Universidad de Birmingham. Y ahorita en febrero se acaba de mudar a la universidad, a Italia, a trabajar a la Universidad de Bolonia como profesor. Entonces, por eso, si vieron el cartel, la tenía dos universidades, porque justo en enero dejó de trabajar como parte de la Universidad de Birmingham y ahora está en la Universidad de Bolonia. Al inicio de su carrera, su actividad se concentró en el estudio teórico de la llamada astrosismología y en estructura estelar. Las misiones espaciales que proveen los datos sobre la variación de la luminosidad de las estrellas lo motivó a extender sus estudios a lo que se llama la astereocronometría, para comprender mejor la evolución de nuestra galaxia, la Vía Láctea. Su actividad académica le ha permitido participar en más de 190 publicaciones arbitradas, 12 de ellas en la revista Nature y en las Annual Review de Astronomía and Astrophysics. Para quienes no están en el área, pues esto suele ser importante. Entonces, y sus trabajos cuentan con más de 13.500 citas y muchos de ellos son considerados como fundamentales en diversos campos de la astrofísica, donde ha aplicado diversas técnicas astrosismológicas. Entonces, bueno, obviamente no vamos a hablar todo lo que, de todos los logros del doctor Andrea Miglio, pero pues thank you very much, Andrea, for accepting this invitation for the Mexican Society of Astrobiology. Welcome, and you have the microphone.
Well, thank you very much, Antigona and Miguel, for the invitation. I'm really flattered, to be here. Very happy to give this talk. Now, I understand that the seminar is addressed to, I would say, an audience who is keen and interested in astrophysics, but not everyone has, background in stellar evolution or stellar physics. So the main thing I'm going to do, or try to do, is share, I would say, the enthusiasm that we have in the stellar community, because we have basically found a new way, a new tool that we use to understand stars, and that tool is what we call astroseismology. And so I'll I guess spend perhaps half of the talk introducing what seismology is, making some analogies with simpler systems like musical instruments, if you like, and just understand what that is, and then give some examples on how we're using seismology to, for instance, characterize planets that are being detected around stars other than the sun, how we're using now stars as laboratories where we can test physics under conditions that you cannot quite reproduce in labs on the Earth. And then I'll focus on a few, I guess, results that we've obtained recently about using ages, very precise ages that we're getting thanks to seismology, to understand how our galaxy, the Milky Way, was formed and how it evolved. So let me start just with this sort of figure here of what is a star, and you can think of a star just as a sphere of gas, and so that sphere acts as a propagation cavity. for sound waves. And as I would say, as a musical instrument, also a star, depending on its size and its composition and how the temperature changes in the star, can have resonant global oscillation modes. So primarily sound waves that, if some conditions are met, they will be trapped in the stellar interior, and then we can measure the sort of surface manifestation of these oscillations by monitoring the brightness of a star. So you can basically stare at the star with a satellite like Kepler or Corot or TESS, and you can measure how bright the star is as a function of time. And if your instrument is sufficiently sensitive, then you can measure these tiny changes, which are in some cases of the order of 1 part per million. And these changes are the sort of surface manifestation of these global resonant modes that are excited in some stars. So what we're doing is primarily we build a model of a star using all we know about physics that is relevant in a star. We build this model, so you have basically a structure in equilibrium, and then you perturb that structure. You pinch the structure basically, and then you can compute numerically with computers, which is the sort of list of frequencies that this model will oscillate with. And then we take the observations, we compare the two, and we use that process to understand what's going on inside stars with very high detail, as I will try to show you. Let me start with an example. Don't worry about the equation really or the details here, but just think about the sort of simplest possible analogy to just an organ pipe. So you have a pipe which is, let's say, its length is capital R here, and you have a pipe which is closed at one end and then is open at the top. And then you can mathematically write down an equation that will describe the behavior of sound waves inside this organ pipe, and you can show that if the pipe has a finite length, as it is the case here, then and the sound speed inside the pipe is uniform, say because the temperature of the air is uniform in the pipe and the chemical composition is uniform, then you have that you can find basically global or resonant frequencies, which will be the sound waves that an organ pipe will emit, which will be equally spaced. So you have a set of frequencies, harmonic frequencies, as in typically in a musical instrument. But then what's interesting is that the distance between these consecutive frequencies is telling you something about the time it takes for a sound wave to propagate inside that instrument. So if you have an instrument or an organ pipe which is longer, then of course the pitch of the sound would be lower. And if you have a smaller pipe or a tiny musical instrument, you know that the frequency is going to be higher. And so this distance between frequency, which we call here delta nu, just a frequency difference, is telling you, as I said, something about, for instance, how big your musical instrument is. And the same thing actually applies to stars. Sorry. Here, I'm just going to show you an example of this is real data from our sun. So the sun has been observed now for decades, since the 1960s. People realized that you could detect these tiny changes in the brightness of the sun, or I would say movement at the surface of the sun, which are actually due to these global oscillation modes. And if you plot the frequencies of these modes, here, let's say the power, so how much energy is in each of these modes, you see that they're quite regularly spaced. And you see this pattern, which is sort of like a comb. And it turns out that the distance between these consecutive frequencies, which we call, again, delta nu here, is again related to how long it takes for a sound wave to propagate from the center of the sun to the surface and then back. And that tells you already, you can show that tells you something about the mean density of the sun. And if you know the mass, well, you can use that to say how big the sun is. Well, for the sun, we have other ways of telling that, of course. But if we can do the same in other stars, then you can learn about the size of a star as you would learn or infer the size of a musical instrument based on the resonant frequency. So that is sort of the simplest approximation. But the I guess the information that is carried by the oscillation modes is so much richer than just the size. So if one sort of takes a step back, and you don't need necessarily to think about stars, but any resonant cavity or anything that generates sound or that has some sort of resonant waves in it, the sound that object, the sort of characteristic sound, will depend first of all on the shape of the object, right? So the geometry of the cavity. Then it depends on the size. So smaller, of course, instruments have a higher pitch, and then the bigger ones a lower pitch. Then, and this is something that happens in stars rarely with instruments, but you can have multiple cavities, right? You could think about sticking together a drum and a violin, right? So you have two instruments, and the sound that this object will generate, I don't think anyone ever tried for good reasons, but it's a sort of combination of these two cavities. And the same happens in some stars, where you can have modes that live in different regions of the star. There are modes that live in the core, others that live in the envelope, and what you observe at the surface is sort of the result of the combination of these cavities. And then another sort of information that you can get from this, from the frequencies of oscillations, is if, say, the star is moving. I guess if the whole star is moving away from you or towards you, and we all, I guess, know an example of the Doppler effect with the usual example of if the sound that is emitted by an object is moving, that object is moving away or towards you, then the frequency of the sound will change. But stars, on top of moving away or towards us, they also rotate. And that rotation has a velocity, of course, and that velocity changes oscillation frequencies. So that is also something we can say or tell about the star, whether it is rotating in its interior, because the frequencies of oscillations of this, sort of the analogy of if you like, a starquake, an earthquake, sorry, in a star, if you like, by measuring these frequencies, we can say a lot really about stars. Another example is that, and that's quite sort of peculiar or specific to seismology, is that if you have, say, in a star, the structure or the sound speed is not smooth, but you have, say, a region where there's a very sudden change in the density or in the chemical composition, that sort of sharp variation leaves a signature in the frequency and in the sound that you sort of can measure from the star. So you can use that to understand, to really look inside the structure of a star. So the first thing, but just very quickly, of course, the spectrums of frequencies of an object will depend on the shape. So if you have a string, if you have a drum, or if you have a sphere, the oscillation frequencies will be different. And of course, the case where sort of more relevant for stars is the typical oscillations of a sphere. And you can have oscillations that are very simple. So these ones here that I'm pointing right now, these are called radial oscillations. So you have basically the whole star that contracts and expands periodically. But then you can also have more complicated patterns of the oscillations. And that's something we understand quite well. And there's ways mathematically of describing that. So you can show that you can basically define a, sorry, something went. Can you still see my screen? Yeah. So that you can, looking at, I guess, stars, since they are spheres, you can identify or define a mode if you define two integer numbers, so L and M. This is just a property due to the fact that stars are spheres. And this is mathematically is the same sort of explanation that is that we use to understand or describe the energy levels in hydrogen atoms in quantum mechanics. It's basically the same mathematics. But that's something we understand quite well, right? So that tells you a little bit about these patterns. But the really exciting bit comes not, or basically the patterns at the surface, but due to the fact that these modes, they actually propagate inside the star. So what we really do, and that's really, as I was saying, the sort of the novel part and the exciting bit, is that we can actually do a some sort of ultrasound, if you like, of the star. And so we can understand and see what's in the stellar cores in some cases, which would be impossible if we didn't have seismology, because all the light that we receive from stars, it originates from the very surface. So the only way we have of really looking into a star is through seismology. So what I'm going to try here is to give you just some examples of this, but adding some sort of sounds, so this sonification of oscillation modes in stars. So what I'm doing is something that is quite simple. So I take, in some cases, just the data. So I know from the observations from Kepler or TESS or Corot, which are the oscillation frequencies observed in a given star. And these are sound waves. But unfortunately, the frequencies of these waves is too low to be heard by the human ear. So what I do is I just multiply or rescale all these frequencies by a factor around 1,000,000, so that they become audible by our ear. And just going to show some examples of what I meant earlier on. Okay, let's start with this is a plot that is very well known within the stellar community. But what I'm basically showing here is, here on this axis, you have the luminosity, which just tells you how much energy a star radiates in a given amount of time. And then on this axis is what we call the effective, or anyway, the surface temperature of a star. And stars, they are distributed in ways that follow these sort of lines, which tells you basically how old or how evolved the star is. And so a star, they're basically born on what we call the main sequence of their evolution here, and then as they grow up or they get older, they move up this branch, which we call the giant branch. So stars, in general, they get bigger as they get older. And so what I'm doing now, I'm just taking a star now, this blue one, and I'm looking at the oscillation spectrum here. And this is basically how much energy is at a given frequency. And here's the typical comb-like pattern. You can still think of these stars as organ pipes, right? So you have an organ pipe which is quite small here, and this is very similar to the sun. And now I'm just going to play the sound from this data, which is not very pleasant, I know. And what you hear is really it's basically these frequencies, and then some beating between these frequencies. And then what happens if I look at the star which has become bigger? So I take this green star, the frequencies, they're smaller because the radius, so the size of the star has become larger. And so if I take the data and just shift them to the audible range, you see that just the pitch of sound has become lower. And that is just a direct way of hearing that we're looking at a star that is bigger. So this is just a sort of simple effect that these oscillation frequencies will tell you something about the size of the star. And then, okay, you can continue and move to these giant stars, as we call them, and then the pitch will go even lower. But that, I'm not sure if you hear it. That really depends on your speakers. Well, the frequencies are becoming very low. So this is one effect. And now I'm going to make a point that finally connects this seismology to the ages, which was also in the sort of the title of the seminar. So what I'm going to show you is, well, these are 3 plots. What I'm showing again is I take it as a proxy or an indication of the luminosity of a star, the brightness of a star, as a function of its color or its surface temperature. And these are plots or data from 3 different clusters. So a cluster is basically an association of stars that were born at the same time and from the same cloud of matter. So they have the same composition, same chemical composition. The difference between these clusters is that this is the oldest, so it's about 8 gigayears. This is 2.5 gigayears, and this is relatively young, so just 1 billion years old. And then what I do is take stars that have the same radius, so they have the same size. But then what changes there, as you see, so this is the sound generated from the data for a star which has a radius or a size which is 10 times the sun. It's a very old star. Now, if I take a star from this cluster here, and now it's same size but younger, then you'll hear that the sound is quite different. I mean, to a level that it's obvious when you hear it, right? And even more if I take, you know, a younger star. So what is the effect here? What happens is that now I've basically fixed the radius, so the size of the star is the same, but what changes here is the mass of the star. And this is something that seismology can tell us. Now, how do we go from a mass to an age? That one needs a little bit of stellar evolution theory, but it is sort of well known or understood, I would say, that say the star spends a relatively short amount of time in this phase, which is this giant phase. They spend most of their time in what we call the main sequence, which is the same phase as the sun is in. So when a star is burning hydrogen in its core. And so it is known that the duration of this main sequence phase depends very strongly on the mass of a star. So basically, when you observe stars here and you can get their mass, well, their age is still going to be determined by the mass. And so this is what is really sort of changing the way we do things now with this data, because we can, for tens of thousands of stars now, determine and measure their masses, which wasn't possible before. And hence, with these masses, we can get very precise ages. So this is why, one of the reasons why the seismology and these modes are really changing or having an impact on different areas of research. And then, well, this is just probably a minor point here, but if you look at the cluster, again, all these stars have the same age. So they're basically going to have the same mass. And this is what we thought. But then when you take the data from Kepler, you analyze them, and then you play the sound of these stars, you hear that, you know, most of them just sound the same. But then every now and then you have these sort of weird stars or unexpected stars. And these are stars that have either lost a lot of mass or they have accreted a lot of mass. And so we're seeing basically the products of when stars are born, say, not in isolation, but they're born with a companion, with a binary star. So it's a binary system, I would say. Then in some cases, what happens is that when one of the two stars will start to become very big in size, then the other component will start basically accreting mass from that star. And so the mass of the star that initially was, you know, less massive becomes bigger. And so you can find these products of binary evolution, as we say, in these clusters. Again, because you can measure the mass, or, you know, just by listening really to the sound of these stars. Right. This, again, without bothering looking at the details, but in stars, for now, I've been talking about sound waves and pressure modes. This is fine. It's something that we sort of all have an idea about, right? In stars, there's also another family of pulsation modes, which we call gravity modes. And these have nothing to do with gravitational waves. So this is much less, you know, exciting to some extent. But these are waves that are, I'll say that the restoring force of these waves is buoyancy. So it is the, well, let's take an example. Is just if you have a cork from I guess a bottle of wine, you know, if you put it underwater, it will eventually be pushed up by Archimedes' push, and it will oscillate around that position. And this is basically what the gravity mode is. Why am I saying that? That's just to make the point that in some stars, especially these red giants, these evolved stars, you have a situation like this one here, where you can have within the same star an oscillation mode that behaves like a sound wave, like an acoustic mode in the envelope, in the outer part of the star, and then it behaves as a gravity mode in the core, in the very dense core. And so this is what gives rise to these coupled oscillators, and we call mix modes. And if you observe stars that have, for instance, they can have the same size, the same radius, the same mass, but they can be in different states, evolutionary states in their lives. So some of those can have a very, very dense core, and they have basically a core which is made of helium, and they're burning hydrogen through nuclear reactions at the edge of this core. And this is one phase of evolution. There's another phase of evolution where the star is actually burning by nuclear reaction helium into carbon and oxygen. And if you look at, I mean, these stars from the surface, they're going to be the same. So you cannot tell the difference really. But seismology and these oscillations modes will have a very significant difference in their spectra. And in this case, if you have a star in this first phase, what you have is a simple, again, this very regular pattern. So if you translate it into sound, again, it's sort of usual boring sound with some beating. But if the star is in this core helium burning phase, then the spectrum is much more complicated. And again, if I sort of sonify that, you might sort of hear that it's not as regular as before. And again, this is if I'm sort of simplifying the spectra, not to make things too complicated, but if you took the data from Kepler, it would be the same. So it's really something that it's a very striking and very clear difference. And it's just by using the fact that these sound waves and gravity modes, they propagate inside the star, and they can tell you something about the very core of a star. And then I think I have a last example on this, of this sonification, is, as I was saying earlier, on the rotation. So if you look at, say, a star and you assume that it's non-rotating, so it's fixed, there's no velocity fields, then there's, say, it has one frequency, and well, the sound is just one single frequency. If that star rotates, or if the core of the star rotates, then what happens is that this frequency will be split into 3 components. And again, here the analogy can work if you're a little bit familiar with, I guess, atomic physics or the energy levels in an atom, is the Zeeman effect, if you like. So if you have an atom where you don't have a magnetic field that breaks the spherical sort of symmetry, then you have frequencies that are degenerate. But then if you had something that breaks this spherical symmetry, for an atom could be a magnetic field, for a star could be the rotation, so velocity field, then these frequencies are split. And what's very interesting is that the size of this splitting, so the distance between these frequencies, tells you how fast the core or the star is spinning. So this is for a star or a core that has a rotational period of about 60 days. Then if I make that core spin faster, then this splitting, so the distance here will increase, and which you can also hear again in the beatings, if you like. But this is exactly how we what we do to infer how fast the core of a star is rotating, by measuring this splitting in the frequencies. And so in reality, of course, when you deal with the model of a star, things get a little bit more complicated, but sort of the basic ideas are explained, I think, by the sort of simple analogies. Yeah, and that's how we get to infer the rotation rate. Okay, I know it's probably a lot to take in, but I think that the easiest really is not necessary to think that these are stars, but to think these as just some simple musical instrument, and then all the information you could have about the size, the shape, and the properties of a musical instrument just by hearing the resonant frequencies. So that, I think, concludes the first part of the talk, where I really just wanted to introduce some concept of seismology. Now what I'll do is just show some examples of some recent studies to show you why is it that seismology is important in astrophysics somehow. So the first example is the impact on studies of exoplanets. And that, I'm just going to have a slide or two on this. The main impact is that with seismology, of course, we can get much more precise radii of stars, ages, and masses. And this, of course, will indirectly help us characterize exoplanet systems. One example, which is typical, is if you detect a planet around another star using the so-called transit technique. So what you do is, again, it's quite simple. You have your star. Then, if you're lucky, if you have a planet that transits in front of the star, in between basically you and the star, if you monitor how bright the star is, then you will see that the brightness will have a dip, so it will decrease at some point because the planet is basically, you see the shadow of the planet on the star. But to infer how, say, the radius or how big the planet is, what you have is this transit depth, as it's called. So there's the depth of this minimum here. But that depends on the ratio between the surface of the planet and the surface of the star. So you need to know the surface of the star, so the radius of the star with very high precision to know how big the planet is. So that is an example. But also the age is becoming very important. And an example of that was a paper led by Tiago Campant, where we could find a planetary system of very small planets with Kepler, and in a star which turned out to be very old. So this is about 11 gigayears, so more than 10 billion years ago, while the sun is about 4.5 billion years old. So this basically told us that planets have been forming around stars since the sort of early times of our galaxy, and that actually when the sun was born and the Earth was born, these planets were already older than the sun is now. So one can also then get excited and speculate about, looking at planets around old stars. Maybe there's been enough time to develop civilization if that ever happened. So it is important to get very precise ages, also to characterize and understand planets. Now another example here, before I get to the to what I'm actually working on in the last I guess couple of years, is to use stars as laboratories. So sometimes the physics that we use in the modeling, it's something we can't quite test in labs, in laboratories on the Earth. And now we're at a point where we're starting with all these constraints to use stars really to understand better the physics that is relevant there. This is an example. It's been probably one of the nicest results from Kepler. What has been possible there is to measure how fast the core of stars rotates as they basically evolve. So this is the frequency of rotation, so how fast this core rotates as a function of the radius of the star. So the evolution goes this way. What one would expect is that what happens there is that the star expands, but the core of the star contracts. It becomes much denser and smaller. So if you think about, angular momentum, if you have a core that becomes smaller and the mass is the same, that has to spin up. But what was observed with seismology is definitely not that. If anything, maybe it actually slows down. And we still don't understand what's going on. But it has to be some sort of mechanism, that is some viscosity, that is able to basically to extract angular momentum from this core that spins very fast and redistribute. So this is just an example, basically, of saying with these pulsation modes, you can measure also the rotation inside stars, and we've found out that we don't understand anything about rotation in stars, because there's no models, even after a few years now, that can explain what we see in the data. And this is another example, which I don't know, maybe it's a bit technical, but it's related to probably my very first paper as a PhD student. So I'm always very keen to show that. But as I was mentioning earlier on, there are some sort of combination of frequencies that will tell you whether the star is smooth or if it has some sort of sharp boundary in its interior. And now, for instance, we can see very clearly, so you see this sort of periodic component here. This is telling us that inside this star, at a position, which is this green line here, there is a sharp change in the velocity of sound, in the sound speed. This is actually due to, in this case, to helium being ionized. Okay, but the interesting bit is that you can really see where this happened in the star, and that can tell you a little bit about, say, how abundant helium is in the envelope of these stars, which is hard to get otherwise. Okay, I think that's all the examples. Before I get to the thing that really I'm excited about, anyway, that I've been working on in the last couple of years or so, and that is to basically take these ages that we're getting for stars using seismology, inferring or measuring ages for tens of thousands of stars in different areas of the different places in the Milky Way to try and understand how the Milky Way, so our galaxy, was formed. And I mean, this is a field which is it's huge, and there's people and groups that have tried to work on this from different angles, right? So you could say, okay, let me start with some sort of cosmological simulations of the whole universe, and then I try to see what happens when I start to look at galaxies. The other thing that people can do is to look at galaxies at high redshift. So you look at galaxies that are well, far away, not only in space, but also in time. And you try to understand changes or how the galaxies looked at the very beginning of the evolution of the universe. What I'm doing, and what this is a whole field of research, is not just me and my group, but is to look just in our neighborhood. So looking at stars within our Milky Way, but with very high precision. So trying to use stars as fossils, really, to try and reconstruct what happened in the Milky Way and how our galaxy evolved. And this is a field which has completely exploded in the last, I guess, couple of years. The main reason is that there's a satellite called Gaia. It's a European Space Agency mission that measures the position and motions of stars with very, very high precision. So before Gaia, we knew the, I guess, distances to stars only what we call the solar neighborhood. So very close to the sun. Now with Gaia, we have a map of the stars in the Milky Way. Not all the stars, but a billion stars. And we know how they move as well. And then there's a lot of efforts in trying to measure the chemical or the composition of stars at their surface for a large number of stars. And this is fantastic. But what was sort of still missing is how do you reconstruct the sort of chronology of the evolution of the Milky Way. So for that, you need ages. And that's where seismology really is making a big impact, I would say. And this is, I guess, work myself and then my collaborators have started more than, I guess, 10 years ago. But it all boils down again to this relation I was introducing earlier on, that for these evolved stars, if you have the mass, so this axis here is just the mass of the star. If you know that, then you can get an age very easily. And you can do that for stars that are, say, from less than 1 billion years old up to as old as the universe. So we have now this very large number of stars with good ages. And that, as I was saying, started as more than 10 years ago with the first data from Corot, which was a French-led mission, which really was the first space mission dedicated to seismology. And then we moved to sort of first steps, trying to be a little bit careful on what we were seeing. And it took years and a lot of papers to convince ourselves and people that you can really get masses for all these stars. And now we are at the point where we want to get to even more precise ages. And this is an example just to show you how challenging this is. So so the Milky Way or its formation and evolution, it's something that was potentially, or from what we understand, very eventful, or with a lot of stuff happening in the first 4 giga-years of evolution. And so we're talking about stars that are 10 billion years old. And to be able to see what happens every, say, half giga-year or giga-year, you need to have a precision on the ages, which are the order of 10%. So to have, I don't know, a 1 billion year resolution in age. And this is extremely hard because we're looking at all stars, so 10% is already 1 billion years, but also because the models we use to determine these ages, they're quite uncertain because we don't know stellar evolution that well. So that's what we've been doing. So primarily, so I know this is getting a little bit technical perhaps, but then I'll get to some results quickly. But these are the data we have, and we used to have just use some sort of average properties of these pulsations. Now we're moving to using every single line that you see in the spectrum to really understand also stellar structure much better. And so what we're doing, we have basically a team of people, some that are working on stars and understanding stars, and then the other team that is using these ages to compare with models of evolution of the Milky Way and really understand what happened to the Milky Way to make it look what it is today. And we're looking at stars in different regions of the Milky Way, with initially Corot, then Kepler, and K2, which was the same instrument but repurposed, and now with TESS. So we're really looking at different regions. So we have a lot of stars in what's called the thin disk, or the halo, the thick disk, the bulge. And so we have a few results now. So this is just going to show a couple of these, and then I'm almost done. One example is that, for instance, with combining this seismology from Kepler, some chemical abundances from some surveys like Apogee, and then this information from Gaia, we could, for the first time, determine the age of stars that one usually referred to as thick disk stars, but with a very high precision. And we have hundreds of these stars, and we can really say, look, that population there is, say, 11 giga-years old, 11 billion years old, and the spread in age is very small. So this must have formed initially very early on in the Milky Way. And then another population, another burst of star formation happened. But we're starting to see sort of this effect. And also, if you look at how stars move in the Milky Way, you can see now with these ages that stars, say, they're born very close to the disk of the midplane of the Milky Way, and then as time goes by, their orbits or their movement becomes more vertical. So that's what you basically see here. This is this velocity dispersion. So the vertical motion of stars, they increase as stars get old. But then the thick disk, or what people call the thick disk, is a different beast somehow. So again, this is telling us that these two populations, they really were formed in different events in the evolution of the Milky Way. And now we're looking also at data from TESS, which is an MIT mission that is actually observing now, looking primarily for planets, but at the same time we can use it to measure oscillation frequencies for hundreds of thousands of stars now. And this is looking at stars that are very nearby. But the interesting bit is that although these stars are nearby now, very close to the sun, I mean, very still, a few hundred parsecs or kiloparsecs away. Now we know how they move, these stars, so we know where they came from. And you can easily show that although we're looking very nearby now, we're still sort of sampling a much wider region in the Milky Way, which is basically what this plot is showing. So this triangle here is where the stars are now, where we observe them now, but we know how they move. So we can say, if we look 1 billion years ago, then, well, these stars, they actually came from very different places of the Milky Way. And the last example here, sorry again if I dump a lot of material on you, but this is very recent stuff. This should be actually 2021 or 2020. So we had a paper led by Josefina Montalban, where we look at stars that we know since a couple of years. These are stars that were not formed in our galaxy. So these are stars that were accreted. So that it was basically another galaxy that was eaten up by our Milky Way some time ago. And we can find these stars, and we measure or infer the ages of stars. And we could show that these stars were actually formed when the Milky Way or part of the old disk of the Milky Way was already there. So this is just an example of showing that we have the resolution or in age to say what happened first. And so we can say, well, this what is called this Gaia and Enceladus merger event happens actually after a large fraction of the Milky Way was already there. So this was not the event that generated this population, but it's just an example. And now just to look at the future, I mean, we have a lot of data from a lot of space missions and ground-based observations, but what will happen in a few years from now, is also that another telescope and satellite will be launched. That's called Plato, which is another European Space Agency mission. Now we'll look for planets around nearby stars, but at the same time, this is the mission that can look at a lot more stars. So here, what you see is this magenta field is where Kepler looked at, and this bigger fields is where Plato will look at. So Plato will potentially look at half of the sky, and so we will be able to do seismology on hundreds of thousands of stars. The very last slide, just looking even further in time, there's a lot of excitement about seismology in the community, so that there's a proposal for a mission which will, if ever, fly in, I don't know, 30 years from now. But we've put forward that idea of having a mission and a satellite that will look at, I guess, stars, very metal poor stars, or stars in other nearby galaxies, to do the sort of similar analysis, but on stars that we can't quite find in the Milky Way. Yeah, so that's basically it. So I thought I would start by introducing a little bit seismology with some analogies to simpler systems, just to try and show you how sort of excited also we are in terms of having found this new technique, and then try to give some examples. I understand that we're probably a little bit too detailed or too narrow, but on how seismology is having an impact and is being quite important to characterize planets, to learn about stars, and also to learn about how the Milky Way was formed and evolved. And I thank you very much for your kind attention, and I'm happy to take questions. Thanks.
Thank you very much, Andrea. My image is not yet there, but my face will show up in a minute. In the meantime, yes, thank you very much. Very, very interesting. Before going to questions, I would like to very globally mention that even the studies in a galactic scale are interesting, because I have seen works, not read in detail, that deal with the habitability of exoplanets in a galactic context, and that will require precise stellar ages. So it's very interesting how this method, that, if I remember correctly, started, of course, on the Earth, but also applied to the Sun and then to the stars, right?
Yeah.
Now,
you're right.
We are open to questions. We will start with colleagues from members of the Mexican Astrobiology Society. Let me check the chat, and I will read them. Let me see if there are questions. Luis Miguel Rodriguez says, hello, Andrea, and thank you for your presentation. It was very interesting. My question is, how important is exposing camouflage in star clusters?
I think, well, the relevance there is that if you think about this sort of connection between the mass and the age of a star, in principle, it's very simple, right? You have the mass, you get the age. But if you do have stars that have gained mass or lost mass, then we're in trouble. And there clearly are cases where that happened. And so if you take a mass, say a star that has gained some mass, then you would say, oh, this star is young, but actually it's not young. It's a star that was sort of rejuvenated. And so you can get ages very, very wrong if the number of these products of binary interaction are significant. So there's a lot of, I guess, interest in trying to quantify them. And also, now that we see quite a few of those, there's a lot of interest from the people who work on understanding binary evolution, which is very complicated. There's a lot of parameters to use this observation to constrain their models, which are then used also to predict, say, how many sources of gravitational waves one is going to find, which are usually products of binary evolution. So there's I think a lot of interest there right now with, I guess, impact on the studies of the population in the galaxy, but also on binary evolution, which is really complicated.
Okay, a question from Antigona. I suppose these studies are limited by the precision of the instruments. For M dwarfs, how close should be a star to do asteroseismology? Age of M dwarfs is particularly hard.
Yeah, that unfortunately is something we're not going to solve with seismology anytime soon. There's a lot of that's very interesting question also within Plato. So the preparation for Plato, now there's a lot of course excitement also on M dwarfs, because they're of course in general they're nearby, and you can get, it's easier to find smaller planets around them. But getting the ages of those stars, the oscillations in seismology, they're way too small. So we cannot, even with Kepler or Plato, it's very unlikely we're going to be able to do seismology. So we'll have to find some other ways. One thing that is sort of being discussed is also that in studying populations of stars within the Milky Way and understanding, let's say, the chemical evolution of the Milky Way itself, if we do a good job, eventually by observing the M dwarfs and just their chemical composition, we might gonna be able to say something about their age because they have a certain chemical composition. But seismology on M dwarfs, unfortunately, that's it's too hard right now, and even for Plato, it's not going to be possible.
Thank you, Andrea. Do we have more questions? Questions from the members of SOMA? I don't see more questions. Well, I have a couple while the people decide whether they ask or not. It was kind of impressive to see, for example, the age of that star in which you say it's 11 gigayears plus minus 1. This 10% is really amazing compared to previous methods or previously used methods like gyrochronology. No, I have never made a comparison, and probably you have a better global picture. How astrosismology, ages from astrosismology compare on average to those derived from gyrochronology, for example, for solar-like stars?
Yeah, it's. I mean, one of the problems we have with seismology is that it's very hard to find any other technique that has a similar precision. But that, of course, doesn't really tell you that we're accurate to 10%, and that's really challenging, because for what happens now, I think there's a few people working also on gyrochronology that what they're doing is calibrating the age rotation relation using ages from seismology as the ground truth. So they're using stars with seismology as calibrators, which is fine, but that means that with seismology, we're not going to be able to test the ages against anything else. So it's going to be hard to do that. And that's really, I think, a crucial point, because we have something that is extremely precise, but how can we test that the ages are accurate? That is the big question. But for gyrochronology, I mean, what's been done now is it's basically taking all the stars for which you have seismic ages and, say, a rotational period, and calibrate gyro on seismology. But if seismology is wrong, then we're in trouble. So it's tough.
So it looks
it's really a hot issue and a big problem, which you flagged.
Okay. Yeah, thank you. I had another question, but let me jump to a question from Sandra Ramirez. She says, thank you, Andrea, for this nice talk about your last example with the captured stars by the Milky Way. Is it a real phenomenon? Can really our galaxy capture this star? How can it happen? Or was it a theoretical case just to show the capabilities of your technique?
No, I think what was possible, and that was, I think probably there's a paper already from a couple of years ago. So by looking at the data from Gaia, so primarily the orbital parameters of stars in the Milky Way and their, I guess, their chemical composition, people realized that there's a whole population of stars that is on very eccentric orbits and have a composition which is not typical of stars of most stars in the Milky Way. And so the interpretation there which was supported by some simulations of is a galaxy being accreted and merged with other galaxies, is that was really the evidence for this what's called the Gaia Enceladus galaxy being accreted by the Milky Way. And I think that's, everybody agrees that those stars are different in the way they move and in their chemical composition, different enough that they look like stars in one of these dwarf galaxies. Now, what is tough is to try and understand when that happened, because one could say, well, that was the last main merger, and maybe what we call the thick disk was born because of that merger. And so what we've done, although we only had, I don't know, maybe 5 or 6 stars of this Gaia Enceladus in Kepler, was to say, well, look, the ages of these stars, at least in the relative sense, they're not necessarily older than some of the stars in the disk. So what probably happened is that this merger wasn't the cause of the thick disk being generated. So it's data that it's there's evidence for this merger. I think that's sort of accepted. But then how you interpret that, then you still need some simulations to really understand what happened. But the ages are really helping out, at least trying to set some sort of chronology of the events. But it's really hard, of course, to looking at the Milky Way right now, where you have, I guess, the stars are also mixed with others, to try to go back in time somehow and try to understand the sort of reverse time and understand the various events that made it look as it is. So it's that is really challenging, and maybe there's not even one unique solution as well. So that's where I guess also the comparison with simulations of merger galaxies will help. But thanks for the question.
Thank you, Andrea. I don't see more questions in the chat, and I don't see questions in the chat from YouTube. So I will proceed with my second question, which is more than a curiosity, is that I actually would like to learn how to do at least basic seismology in stars. And the question is, let's say, astroseismology is based on the analysis of time sequence analysis of the luminosity of the stars, no? Where we can see variations of the luminosity. But the question is how the uncertainty in this luminosity has to have a threshold to be able to do something, I guess. And the question is, what is this threshold, for example, in optical light?
Yeah, I mean, that really depends on the stars that you're interested in. I mean, if you, of course, broadly speaking, seismology should also include, classical pulsators. And of course, if it's a Cepheid, then you could do it almost with naked eye for some stars. Depending on, say, if you look at stars, so most of the stars I've been talking about, those are cold stars like the sun. So you have these modes that are actually, so these solar-like oscillations. And the amplitude of these modes depends on the luminosity of the star. So if you look at stars like the sun, it is, a few parts per million. So it's tough. And you need, basically, in photometry, you need to go to space. That is unavoidable. If you start moving up on the red giant branch, so the more luminous the star is, the larger the amplitude is as well. So you can get to, hundreds of micromagnitude too, at some point millimags, etc. So the higher you go in luminosity, the easier. Unfortunately, at least for the giants, the higher you go in luminosity, the less frequencies you're going to see. So that it's harder to get detailed information once you have stars that are very luminous. But there's not, I wouldn't say there's a definite threshold. There's also a limit on on the pulsation periods, right? Of course, the higher you go in luminosity, the bigger the star, the longer the period. So you'll have to have observations that will cover a longer time span as well. But so it's I think depending on the instrument, there's certainly some star that you can get some pulsations out, but the sun-like, the solar-like oscillations, you need to have, you know, I mean, for the main sequence stars, it's micromagnitude, so that's really going to space. And if you, well, Antigona was mentioning M dwarfs, then that's not even from space we can do that. But of course, yeah, depends on the intrinsic amplitude. So.
Yeah, right. Yeah, but just a rough estimate is a few parts per million, let's say.
Yeah, at least for the main sequence stars, then I think yeah, with millimag you can get high up on the RGB. That's still possible.
Mm-hmm. Then I am done because I was planning to use a telescope on the ground, and I don't think we will even reach a millimagnitude in precision. But anyway, it will be fun. Okay, let me jump to another question. Irma Lozada says, "Hi Andrea, thanks for a wonderful talk. My question: what are the major space-related factors generating noise in the H estimation with asterochronometry?"
Yeah, so I would say the main limiting factors now is really the systematic uncertainties from the stellar models themselves. Because of course, usually when you take a grid of models, nobody really changes all the ingredients from the physics. And if you start doing that, then the uncertainties will get much bigger. The hope is that when we look at systems that are very well constrained, such as say clusters or eclipsing binaries, that we can try and I guess reduce some of these uncertainties by testing the model. But it will always have to go sort of hand in hand. The improvement in ages, they can only come from improvements in the stellar models, and that's really the limiting factor. To be honest, the data, especially if you think about Kepler data, I mean, we're still very far from having reached the limits of the data. It's more the models that needs to be improved.
Mm-hmm. Thank you, Andrea, for your answer. And I don't see more questions in the chat here in Zoom, and I don't see questions. I see only thumbs up in YouTube saying that it was a good talk, but no questions from them. And I have no more questions. So I guess we finish here. We thank you very much.
Thanks again for the invite, and thanks everyone for your time. Thank you.
Thank you. I will finish here the YouTube. Let me just check again whether there are questions or not. Nope. No more questions, so I will close the transmission through YouTube. Thank you very much for those who were in our YouTube channel, and thank you also to members of SOMA, and of course thank you very much to Andrea Miglio for this very nice presentation and interesting presentation. Thanks again, and